Hey everyone, welcome to The Explainer. When you or I watch a movie, our brains seamlessly integrate the dialogue with the movement of the actor's lips, literally in mere milliseconds. But for an artificial intelligence, bridging that gap between different types of overlapping data like audio and video is a massive, incredibly complex hurdle. Today, we're diving into this fascinating challenge at the absolute cutting edge of machine learning. We're going to look at a groundbreaking new approach that completely restructures how AI models handle all this messy data.
Okay, let's take a quick look at our roadmap for today. We'll start with the multimodal AI problem, look at where current methods fail, define the ideal AI target, and then introduce the S3 framework, how it operates, and finally, why this all matters so much.
All right, let's jump right into section 1, the multimodal AI problem. So here's the core question we're tackling today. How exactly does an AI make sense of the world when given messy, overlapping inputs? Think about it. When we hand an AI a video file, it doesn't just see and hear the way we do. It gets hit with a chaotic array of pixels, alongside an entirely different array of audio waveforms. These modalities have completely different resolutions, different types of noise, and they capture different aspects of the exact same event. It's a highly asymmetrical environment, and the AI somehow has to figure out what all these numbers actually mean when they're mashed together.
Which brings us to a really crucial term you need to keep in mind, multimodal representation learning, or MMRL. Put simply, this is the explicit mathematical process where learning algorithms determine what data to align, what to keep, and what to throw away from different perceptual channels. Basically, it's the AI's internal logic for filtering through a massive amount of sensory noise to figure out what actually matters for the task it's trying to complete. Now, what's really interesting here is how this illustrates the data breakdown. Notice those overlapping shared factors right in the center? That represents information common to both inputs, like, say, the rhythm of a person playing a drum. That's both visible on screen and audible in the track. But take a look at the outside edges. Those are the modality-unique factors. This is data specific to only one channel. Maybe the video captures the shiny color of the drum set, while the audio captures some random background street noise. The ultimate challenge for the AI is figuring out how to handle both that shared center and those unique outer edges at the exact same time.
Let's move on to section 2, where current methods fail. Right now, we have two dominant paradigms in the field. And honestly, they both suffer from massive blind spots. On the one side, we have contrastive learning. I like to call this one the oversimplifier. It forces alignment between modalities by focusing entirely on that shared center we just looked at, completely tossing out those unique outside cues. On the flip side, we have Infomax. Think of this as the digital hoarder. It tries to fix the oversimplification problem by keeping absolutely everything. And the result? A digital representation that is incredibly cluttered with task-irrelevant noise, which, as you can guess, severely degrades the model's performance. And the danger of that oversimplifier approach really comes down to a strict mathematical principle known as the data processing inequality. Basically, this states that once important information is lost during the encoding process, it can never be recovered by downstream predictors. It is just gone forever. So if an AI using contrastive learning throws away a unique visual cue just because it didn't align perfectly with the audio track, well, that AI is permanently blind to that cue, making optimal performance literally mathematically impossible. So what is the solution? Let's dive into section 3, the ideal AI target. To escape the trap of both the oversimplifier and the digital hoarder, researchers have defined two theoretical pillars for a truly optimal AI representation. The first is task sufficiency. This means preserving absolutely all the information relevant to the specific target task. The second is information minimality, which means strictly excluding all irrelevant noise and variations. In plain English, we want everything you need and absolutely nothing you don't. Simple enough, right? Well, building a single monolithic model that's flexible enough to achieve both of these at once has proven to be incredibly difficult. Which brings us to a major breakthrough in section 4, introducing the S3 framework. Researchers are proposing a framework called S3, which breaks down into 3 very logical stages: specialization, selection, and sparsification. Instead of trying to cram all those messy multimodal signals into one single fixed embedding, S3 completely restructures the whole shebang. It treats the neural network not as a single brain, but more like a mixture of experts. It breaks the data down and dynamically routes it through these 3 distinct stages, giving us incredibly fine-grained control over what information is kept and what is thrown away. Let's unpack how this actually works in practice in section 5, how S3 operates. All right, step one is specialization. Instead of keeping the input as a massive, uniform web, the S3 model explicitly decomposes those raw signals into distinct units. Notice how it breaks things down into concept-specific semantic units, like a single expert handling a very specific type of data concept. By creating multiple specialized components, expert 1, expert 2, and so on, the AI essentially builds a highly structured, distributed semantic space. And guys, this is a massive shift from older methods. By relying on a team of specialists rather than one monolithic encoder, the model can actively mitigate that cross-modal asymmetry we talked about earlier. It preserves those crucial, unique nuances from the audio or the video, but without losing the shared context. It's a real game changer. Now, if you have a team of highly specialized experts, you obviously need a smart manager to coordinate them, right? That brings us to stage 2, selection, managed by the router. The router dynamically navigates the latent space, which is essentially the AI's internal multidimensional map of concepts, and it adapts specifically to the task at hand. It evaluates the data and dynamically calls upon only the specific concept experts required for the job, totally ignoring the rest. It activates just the relevant experts to build a compact, highly focused representation. Finally, we reach stage 3, sparsification, which happens seamlessly in inference time. The model actively prunes away the low-contribution routing paths. Notice how it aggressively suppresses the irrelevant noise, represented here by those smaller, lower blocks, leaving only the highly relevant data paths standing tall. The researchers actually observed a consistent reverse U-shaped performance trend during this stage. Basically, accuracy peaks at an exact optimal sparsity level that kills the noise while preserving the essential signals. It literally hits that theoretical everything you need and nothing you don't ideal we were talking about earlier. So let's wrap this up in section 6, why this matters. Let's look at this key takeaway directly from the source paper. It says, structuring multimodal representations as selectable semantic components provides a practical and principled alternative to contrastive learning or infomax-driven approaches. What this boils down to is that we no longer have to choose between an oversimplified model that deletes crucial data and a digital hoarder model that's just drowning in noise. S3 gives developers fine-grained control over information use, and this is the crazy part, it achieves this super efficient sparsification without requiring any additional training. That is absolutely huge. Which leaves us with a pretty provocative question to wrap up this explainer. If AI can now perfectly balance everything you need and nothing you don't, using a dynamic team of semantic experts, what complex real-world problems could this hyper-efficient architecture solve next? Just imagine autonomous vehicles processing chaotic visual and radar data in a split second without any noise interference, or medical AI cross-referencing patient scans and textual histories with absolute perfect clarity. Structuring AI like a selectable team of experts isn't just a clever mathematical trick. It's a massive leap forward in how machines understand our world. Thanks for joining me today, and keep questioning how the data around you is being built.